Welcome, welcome to the session again. So today we will be talking about the module 4, which is the detection, estimation and the millimeter wave channel, more details into millimeter wave channels. So today we will first talking about the basic ISI channel. The concept that will be covered today is the basic ISI channel model, and then what is the data model with the equivalent Toeplitz matrices. So last class we have talked about the coherence time part, and we did not give any formal definition. We just gave a flavor of what exactly a coherence time means. So I go back to my earlier diagram here. So if you look at it here, I think I have already re-explained. Let me go through again. So here what I am saying is that channel, say I am sampling the data at 10 megahertz ADC sampling, and I am seeing my channel is changing because of the Doppler. Then we said that is the change significant. Okay. If the change is not significant, I should not even care. Now, when I say the change is not significant, with respect to what? Okay, that should be a definition, because significant or not significant is not a mathematical definition. You have to mathematically define what is significant, right? So, can I make this kind of definition? Say I have HL at a particular M at mth point, whatever the definition, whatever the m value, mth time, whatever the channel value. Let us say m plus k. Can I define this as a parameter? It is a mean square error. That means how much it has off by. So, can I define that as a measurement quantity by which I can say channel has changed this much amount, because this is a measurable quantity. Now, can I bound it? So, let us say this is less or equal to some epsilon. Okay. What is the value of epsilon? That comes from your application, right? If it is audio, it may be very large value, because what does it mean? It means that I can tolerate a larger change in channel without doing a re-estimation. If it is like a 4K or 8K video, 8K streaming video, probably epsilon can be even smaller number. I can't specifically say what value needs to be taken, but you can guess the number can be very small, say 10 to the power minus 8 or 10, but it can be some small number, right? Depends on application, whatever it is. Is this a reasonable quantification of my changes of channel, right? So, that means when I say from m to m plus 1, m plus 2, m plus 3 and so on, I say up to 100 my channel do not change significantly. It simply means that take any of them from the first to any of these values, their mod square does not cross my limit epsilon. Okay. Moment it crosses epsilon, I would say at that point my channel has changed significantly. That means if I take the first one, so obviously the change will be from first to the last. So, if I say my HL 0 minus H of L k, so you keep on increasing your k and observe with respect to the first one how much the data has changed, and you define your own epsilon and see whether channel has crossed the limit. The moment at a particular value k has crossed the limit, I would say till k my channel did not change significantly, because my application does not care anything beyond epsilon changes. Okay. Now, this is a big now it becomes kind of a fuzzy, because I do not know. So, that means for every time you have to bring in the application, right? Because unless you specify the application, this does not have any meaning to me, right? Coherence time, because different application needs a different coherence time, because that is what it comes to me. But can I generalize it independent of coherence time, independent of the application? That means no matter whether it is audio or video, but more or less I can say if it goes beyond this time, the channel do not change significantly. Now, what is that do not change? probably it may be just 1% or 2%. So, can I have that kind of definition which is irrespective of any application? Yes, there is a definition for that. So, that definition is basically this one. So, your coherence time is defined as 1 by 4 of your Doppler spread. Okay, that is the real definition. So, this is also a coherence time definition, but this is more of an well accepted definition which does not take into account the application specific case. Now, using this definition we have seen say different cellular standard or whatever, it kind of satisfied most of the applications. Okay, some may be impacted, some may be not impacted, but on an average this is a good definition. Okay. Now, here if ds is a random number, naturally we have discussed this, that this would be again expectation will come into picture. So, this ds is your Doppler spread. So, what is this ds? This is your Doppler spread. This is a Doppler spread. This is a good definition of the coherence time. See, the Doppler spread is a 1 Hz, that means you have 1 second time to 0.25 second time for which channel do not change significantly. Do not change significantly meaning it may be just 1% or 2%, for which most of my application run almost perfectly. Okay. Now, what is the Doppler spread? I think we may have defined it, but for the benefit of this class I redefine it again. The Doppler spread is basically you know the delay spread, right? It is the maximum delay from the lowest point to the highest reflectors point, right. So, similarly there is a Doppler spread also. It is the let me first define what is called Doppler frequency, that has already been defined, I believe. So, let us say fd is the Doppler frequency, it is just a definition. This will be v of the element divided by speed of light multiplied by RF frequency. Okay. Now, Doppler and the difference in the Doppler. So, basically what is the Doppler spread? Okay. So, if you have a transmitter here, if you have a receiver here, and let us say you have one reflector here, and let us say this is the one. This is just one data point, right, and there may be on one data point. Okay. Take again the similar way we have done for the other one. So, take each and every pair of points and see what is the Doppler frequency coming into picture for individual points. Suppose this is static, and this is dynamic. Say this has a velocity v. Okay. So, for this the Doppler frequency would be 0. For this the Doppler frequency would be 0, for this the Doppler frequency would be some fd, right. Okay. Or if this one, say reflector is also moving with some other velocity, say v2 velocity, so this is moving at a speed of v1 velocity, then it will have some other Doppler frequency. So, let us say it will also have a Doppler frequency associated with it. So, every component will have a Doppler frequency. Now, spread meaning it is the difference between that. Okay. So, you take each and every pair, that means this is say node 1, this is node 2, this is node 3. Okay. And take each and every pair, say for pair number 1 and 3, you see the difference between them. Okay. So, it's a take the mod of that positive difference only, f of d minus 0, because this has a Doppler 0, the first one has a Doppler 0. So, you take each and every pair and try to get the difference between their Doppler frequency with a positive magnitude. Take this, then you take the pair 2, 3, you will have some fd1, fd minus fd1, and so on. And similarly, you have for 1 and 3, you will have fd1 minus 0, like that. So, you have 3 points. So, 1, 2, just the way we have done the delay spread, same thing we are also doing it here, just the Doppler spread. Take the maximum of them. I do not know which one will be maximum, depends on what is FD and what is FD1. Let us say this is the high frequency. So, this component will be the highest. So, which means my DS, whatever we have defined it here, this DS is Doppler spread, but of course, the maximum of all the Doppler spread is the max of the Doppler spread. So, you take the max of it. Okay. So, take this, take 1, 2, 3 and see what is the max of it. Okay. And that max, so your DS is basically the max of all the Doppler frequency difference. So, it would be mod of FD, mod of, in this particular example, and then this would be f of D1 minus f of D, like that. Take the maximum of it and whatever comes, that is your maximum Doppler spread. So, your coherence time is a fairly good definition, your expectation of 1 by 4 of this DS number. Why it is an expectation? Because this DS is a random number, right? Because every V is a random number, velocity is a random number. We have discussed this, but nobody moves at a constant speed. Everybody moves in a different random direction and random velocity. So, your Doppler spread will also be random and this will also be random. Okay, so that's the point here. Okay. So, this definition is quite popular, and if we know what is your Doppler spread, then you can tentatively find out what would be the, what is the time range for which my channel remains almost constant. I should not say the term constant. It is like it does not change significantly. Significantly, again, it is application dependent, it is a context dependent, but more or less I mean, no matter what application you take it, it covers most of it. So, this is the classic definition. So, now if I summarize what we have so far learned, I would see that we have now we are now moving to the millimeter wave part, because this is the pillar of understanding. From here, the actual millimeter wave or millimeter definition will start here. So, what we have learned, let me summarize it. So, in summary, we have learned the physical environment, over which the transmission happens, like reflectors, scatterers. What is diffractor? There are 3 type of physical, usually these are the 3 physical blockage will be there. Then what we have learned? We have learned how you can model the channel using ray tracing. Ray tracing, that means just if a ray goes from one point to another, point to point ray tracing. Okay. Then what we have learned? We have also learned using the ray tracing how I can finally model the channel using IIR filter and subsequently an FIR filter. How do I get IR to FIR? You just take a window, you get an FIR filter. Then we have learned how the channel models vary from analog to the digital part, right? Because that's where our another interest was. So, channel model analog or RF, and this is your channel model digital HLM. This is what we have learned it. Then we have learned some of the parameters. What are the parameters that you need to consider for channel? So, before parameter, the statistics part. Statistics of what? Statistics of individual channel type, and we have shown that if I follow more or less the central limit theorem, they will be zero mean Gaussian, cyclic symmetric, zero mean complex Gaussian noise, complex Gaussian channel. Then we have learnt the parameters. Parameters in the sense that we have learnt what is called coherence bandwidth. Coherence bandwidth is what? It is the actual bandwidth of the channel that comes into picture. Then we have also learned what is called a frequency flat fading and frequency selective fading channel. That means if it is a coherence bandwidth is more than your actual system bandwidth, I will just see one tap. It is a flat fading. That means as if like my channel has infinite bandwidth. So every frequency component of my data is facing equal amount of gain from the channel. It is a flat. Then we have learnt the coherence time. Then we have learned what is called Doppler spread. Similarly, we have learned what is called delay spread, because these are the parameters which will be left and right used in the channel. So far, these are the parameters that we have learned, but as we move along, there are some more parameters which will appear. They are called angle of arrival, angle of departure. Those will come into picture. So far, that we have not considered, but these are the basic models that we have considered. So, in summary, there are 9 points that we have discussed here, and we have also discussed the time series part. So, I should not write 10th model, because that is like a mathematical tool by which you can model the Doppler or a time varying case here. Okay. Now, let us move to the millimeter wave. So, this is the foundation. Now, this foundation works for most of the channel case, but then what will be the different scenarios when I change my RF from just 610 gigahertz to say 40 gigahertz, 60 gigahertz or 100 gigahertz or even more, okay, millimeter wave or terahertz kind of. What exact changes that appear here? We need to now understand it. Okay. Now, before we get into that, let us understand step by step, because this is the first foundation. A second foundation is that why should I go into millimeter wave? Why should I go into the higher RF? Okay. So, let us start that part. So, whatever parameters we have defined, whatever methods we have defined, they all hold good, equally good, probably better for any RF. They do not change. Over and above, some extra thing comes into picture. That is the reason we have so far covered this foundation part. Now, we are getting into the millimeter wave models. Now, before I get into the millimeter wave model, let us understand what is the physical point or the physical systems that it offers. The physical system in the sense, the environment, the reflector, scatterer, those things, what they offer to us. Okay? Because unless you know them, there is no question of modeling, right? And if I do not model, I cannot do a signal waveform generation or do a signal processing. So, let us understand that physical part of it. So, that means when I say millimeter wave, it essentially says that my FC is greater or equal to 30 gigahertz. Okay. So, what is millimeter in this case? It is the lambda. So, for 30 gigahertz, what is the lambda? Okay. It is sub 1 centimeter. That means you have to express it in terms of millimeter. That is why it is a millimeter wave concept. Okay. That means it will be less than 1 centimeter. Okay. So, I have to say it is a 5 millimeter, 2 millimeter. So, I have to express the lambda in terms of millimeter. Okay. Because it is no more a centimeter. It is a sub centimeter lambda. So, that is why it is a it is a millimeter wave concept. So, now suppose I change my RF, and why people want to change it. I think we have discussed this part, why people want to go for higher RF. The higher RF advantage is that the availability of bandwidth. That is fine. That is the first key aspect that comes into us, right? Because if you look at the 10 gigahertz space that is available in a particular region, you will see that most of the places, up to 10, 12 gigahertz, it is auctioned fully. Okay, so it is not available. The space is not available for any more transmission. Now, we need to go for a 5G or even after 10 years 6G and so on and so forth. So, what is the spectrum? The spectrum is not available, right? The spectrums are completely auctioned and they are utilized. So, if the spectrum is not available, there is no question of bandwidth also available, because you may get some spectrum here and there, but the bandwidth may not be available. Right. Suppose you may get something at say 9 gigahertz, and the amount of bandwidth that you get, say just 2 megahertz bandwidth that you get. So, what is the use of it? okay, because we are talking of 5G, we are talking of 1 Gbps, 10 Gbps data link. So, if you have that level of data link, I mean, with using that small amount of bandwidth is not good enough. You have to increase your bandwidth as well, right? Because it has, your capacity of your system has to increase. Unless it increases, there is no point. So, obviously, I need a larger bandwidth. Okay. Now, when you say larger bandwidth, the concept comes that where is it available? Because up to 12 or sub 6 gigahertz, I do not have any higher bandwidth available. So, then obvious natural push is that you have to go for a higher RF. So, you increase your RF, So, 30, 40, 60, 100, whatever. I mean, sky is the limit. You can go as much as you can go. So, and that is what the push is for. So, now what is the advantage of going so high? Advantage is that bandwidth itself is available. Say for example, I am at 60 gigahertz RF, or I am at say 120 gigahertz RF. Okay. How much bandwidth available? Around 60 gigahertz, plenty. Probably 1 gigahertz, 2 gigahertz bandwidth is available. At 120 gigahertz, how much bandwidth is available? To the best of my knowledge, I don't know if anybody has ever utilized that bandwidth for commercial transmission in a cellular or any Wi-Fi. No, nobody has used it. So, it is available fully. So, even if I take say 10 gigahertz or 5 gigahertz bandwidth, probably it is okay, even that. So, that means if I go for a higher RF, as it is not auctioned, people do not use that, except some places military and all, radar and all. But most of the time and most of the places, the higher RF is unutilized. So, I can utilize a higher bandwidth as well. So, that means I can go at 120 gigahertz RF and I can create a signal which is almost 10 gigahertz. Okay, I can have it because nobody has done it. Now, is it as simple as that? Is it as simple as just going to the higher RF and utilizing the whole bandwidth? Probably no. What are the bottleneck here? The first bottleneck here is that moment I increase my RF, what are the channel model changes that come into effect? If you remember, the way we have done a channel model, ray tracing model, it is a very generic model. So, even if you go for terahertz or whatever frequency go, whatever we have explained so far, that same thing holds true. There is no difference. The only thing is that if I increase my bandwidth, some of the things will break down, and what is the remedy for it. But in some sense or the other, the same model, whatever we have discussed, the same thing I can utilize it. Okay. Now, we need to understand where something, I just said that what? Something breaks. We need to see that where something breaks. But if something breaks, can't I use that model, whatever we have discussed? I would say yes, you can still use that model, whatever I have discussed, but with some sort of a small modification. That I will explain it. Now, let us see if I go for a higher RF, what is the problem? Problem was that obviously your range will not come into picture, because if it is a 6 gigahertz, your range was very high, right? If you look at 3G or 4G base station, it has a very tall base station, and what is the range? Some kilometer it can go, right, range. But if it is 120 gigahertz or say 60 gigahertz, forget about it. No way it can go up to kilometer, probably few hundred meters. I don't know, probably 200, 300 meters, or even it can even move. Maybe if it is 120 gigahertz, it can go even for few meters. You can calculate how much it can go. So, that is a big problem, right? So, if I go for higher RF, the problem is that my path loss is very huge. So, this is a problem for millimeter wave. A second bottleneck which appears to us is that path loss is huge, fine. What about the absorptions? Because if it increases the frequency, the environmental components will do a worst, I would say. I mean, it will create a havoc in terms of the absorptions. I think I may have shown you some of the absorptions scenarios. If I look at the gain, received gain versus other frequency, there was a famous diagram which will show you like that. If you go higher RF, the dips will be much more. Okay. So, these are around 60, this is I think around 80, 90, I am not sure, I need to check that. And there are many such, there are laundry list of points where the dips are there. Okay. So, these dips will now come into picture. If you go into higher RF, these dips are very frequent. Okay. So, even if you want to utilize say larger bandwidth, you have to be careful that you are not into any of the dips. So, why these dips happen? These dips are due to the resonance of the material through which the RF is going on. Okay. So, for example, if there is materials are, I mean air may have a different material, carbon dioxide, oxygen, sulfur dioxide, water vapor, all these other, they have a certain resonant frequencies and they are like a different resonant frequency you will have. So, if RF comes out to be of one of those resonant frequencies, that whole RF will be completely killed. So, that means that particular material will absorb the whole RF. That is why this dip comes into picture, right. So, this is one issue. Now, apart from even a dip, this dip comes whenever there is a resonant frequency, but apart from that, what about these? What about these? They are not just due to the path loss, they are also due to the absorption. It means that if you increase the RF, the absorption by a normal material will also increase. That means a material which probably do not do much absorption at say 5 or 6 gigahertz, but it will show some sort of a larger absorption when it goes up to say 100, 120 or 200 gigahertz RF. It is a property of the material. I think I may have shown you when I was characterizing the the alpha part, the gain part of the channel. It has 3 components, right. One is a path loss, one is a absorption coefficient, another one is the phenomena dependent, right. So, this absorption becomes very prominent when I increase my RF. Second part, a third part. A third one, and which is also another issues. Third one is what about the number of reflectors and scatterers? So, on what basis some object acts as a scatterer or a reflector or a diffractor? It depends on the dimension of the material or the object with respect to the lambda. Suppose my lambda is say 10 centimeter, then I am sending an RF whose lambda is 10 centimeter, but I have an object which is just say 2 millimeter object, small 2 millimeter object. Will it create any trouble for this particular RF? Not much, because its dimension itself is very small with respect to lambda. Does it act as a reflector? Well, may not. Does it act as a scatterer? What it will scatter, because its dimension is so small, just only a small blockage will be there. It will not create much hindrance to it. But what if I have an object which is of the order of 10 centimeter? Will it act as a reflector? Yes, now it will act as a reflector. Will it act as a scatterer? Well, it depends if the surface is smooth or not. Again, we have also explained the smoothness again is a relative parameter. Okay. Say for example, I have a surface like this and this surface is something like this, slightly rough. Now, whether it will be a rough or not, again it will be decided by lambda. If the lambda is large, probably this small ringle will not create any problem. This will just act as a reflector. Whereas, the same surface will act as a scatterer if the lambda is small. Suppose if you look at this ringle, small dips, what is the dimension? Probably a fraction of millimeter, probably 1 or 2 millimeter. Now, if the lambda is of the order of also 1 or 2 millimeter, then each and every dips will act as a individual small what? Reflector. So, that means as a whole it will act as a scatterer. That means if the ray falls here, every fellow will now start to deviate the data from all directions. So, this is becoming a scatterer. Scatterer is more dangerous than the reflectors, right. So, these issues now come. you may see more and more reflector, more and more scatterer. Probably I will say more and more scatterer, because every tiny object now becomes a scatterer. Every surface which you didn't think that can be a rough surface. You may think that it's a very smooth surface, but now that will become a rough surface whenever you decrease your lambda. So those issues now come. So that means the phenomena related issues are now becoming these phenomena dependent issues are now becoming again prominent. And I mean every point whatever we have discussed for the gain part all now become very worse when I increase my RF. Okay. So I'll stop it today. In the next class we'll take these points and try to see what happens in the millimeter wave, how these points can be tackled. Okay. All increases, but how we can tackle this, and finally what will be the right model for the millimeter wave, and if I increase the RF say terahertz or so on, how the modeling will be coming into picture. This is the reference Statistical Signal Processing volume 1 and 2 by SMK. Okay, with this I conclude the session here. Thank you.